My wonderful chemistry students, AP Chem students, we are diving into Unit 7. Okay, so Unit 7 is all about equilibrium. Equilibrium reactions are reactions that go both in the forward direction and the reverse direction. And we're going to see when the rate at which the reactants turn into products, when that equals the rate at which the products are turning back into reactants, that's when equilibrium is reached. So that's what this entire unit is about. So let's dive in. So I'm on page 5. Actually, let's keep going. Let's go to page 6. Okay. So like I told you, we are specifically dealing with equilibrium reactions, like reactions in which it is both forward and reverse. So if this is the forward reaction in which water liquid is turning into water gas, so H2O liquid is turning into H2O gas. So we have this forward reaction. I want to show you a couple different ways that you're going to see this. So forward reaction. And then also the reverse reaction is happening where the gas is turning back into the liquid. So that means we have reversible. Okay, so lots of different ways. Double-sided arrow. Another one is like 2 arrows. Okay, third way is this guy. So all of those are like the double arrows, this equilibrium, where both the forward reaction and the reverse reaction are happening. Again, when the rate of the forward is equal to the rate of the reverse, that's when equilibrium is reached. So a reversible reaction doesn't have to be in equilibrium. It usually doesn't start in equilibrium, but it's going to achieve, if left alone, if no stresses or anything are added to it, it's going to keep bouncing back and forth until it finds this equilibrium point. So again, we have like NaCl, solid, turns into NaCl aqueous. We dissolved it in water. Other thing, even though this reaction happens both going forward and going in reverse, the left-hand side we call reactants and the right-hand side we call products. So even though it's products turning back into reactants, I wouldn't all of a sudden call these reactants as well. So when we're talking in class, reactants left-hand side, products right-hand side. So we're going to have this equilibrium, this back and forth reversible reaction where x plus y turns into xy and backwards. And we want to know if or when equilibrium is reached. And so we're going to look at each kind of time frame here. So do you see how going from time 0 to time 100 seconds? So what we start off with here is only x, and let's even talk about how many. So there's 1, 2, 3, 4, 5. So there's 5 x reactants, and then there's 1, 2, 3, 4, 5, 6, 7 y reactants. So that's what's happening at time 0. Now let's look at time 100. In this one, there's still some x in there, 1, 2, 3. And then there's still some y in there. Oh, I didn't leave myself a lot of room. 1, 2, 3, 4, 5. But then we also have this xy product, and there's 2 of those. So what does that mean we're favoring right now? Is there more forward or is there more reverse reactions happening? Forward reactions mean that what we are labeling as reactants are turning into products, where reverse reactions are products turning back into reactants. So do you see how we started with 0 of these products? And then when some time passed, we made some of those? that would only be happening if we were favoring the forward. If this forward reaction was happening at a faster rate than the reverse reaction. Are we making more of these than are being consumed? So we have not gotten to equilibrium in this time frame from 0 seconds to 100 seconds. Instead, what the amount of items are telling us is that reactants are going away and products are being made. So reactants are going away and products are being made. That's a forward reaction. So from time 0 to time 100, we are favoring the forward reaction. Favoring the forward reaction. And again, everyone, in a forward reaction, we have reactants turning into products. So essentially what's happening is the amount of reactants are decreasing and the amount of products are increasing. Now let's look at time 100 to time 200. So we know what's happening at 100. Now let's see what's happening at 200. Okay, there's still some X in there. There is 2X in there. And there's still some Y in there. 1, 2, 3, 4 of those. And then these XYs. Now we got 3 of the XYs. So do you see how going from time 100 to time 200, that the amount of reactants are decreasing and the amount of products are increasing? That is only the case when we are favoring the forward reaction. When forward reactions are happening more than reverse reactions, reactants decrease and products increase. So we're still favoring the forward. Okay, now we're going to go from time 200 to time 300. So we know what's happening in 200. Now let's look at 300. So there is some X in there. There is some Y in there. And we got this XY product. So there is 2 X reactants in there. There's 1, 2, 3, 4 Y products. And there's 3. Hold on. So 1, 2. Okay, and then Y, 1, 2, 3, 4. Okay, and then 1, 2, 3. Oh, interesting. So when we went from 200 to 300 seconds, do you see how this exchange essentially halted? It didn't actually stop, but it's because the rate at which the forward is turning into products, reactants are turning in products, is equal to the amount of products turning back into reactants. That's why the amounts or the concentrations of these have stopped. That we had 2 X items and we also had 2 X items, and then we had 4 of the Y's and 4 of the Y's, and then 3 of the products and 3 of the products. That is only the case when equilibrium is reached. So from 200 seconds to 300 seconds, we've reached dynamic equilibrium. Okay, that although one of these and one of these turns into one of those, like that happened, one of these also went back to those items. And so this back and forth is equal. The rate at which these items are turning into those items, back and forth, is equal. So the concentrations, the amount of these things, do not change. Now let's see if it stayed in equilibrium. So we got X, we got Y, and XY. Okay, let's count this up. There's 2X, oh, that's looking promising. There's 1, 2, 3, 4 Y, and there's 3 XY. So we are still in dynamic equilibrium. Okay, now whether dynamic equilibrium was reached by 400 seconds or not, draw the particle diagram for 500 seconds in which equilibrium is established. And I'm going to let you guys do that, and then actually we'll check it in class, or we'll draw it during class, so we'll come back to that. Nice. I do want to add one thing. Sorry, page 6. This is favoring the forward. So if we're favoring the forward reaction, reactants are going to go down and products are going to go up. If we are favoring the reverse reaction, reactants, products, that's when products are going to go down and reactants are going to go up. And we didn't see any of that. We didn't see any favoring of the reverse. Okay. So that's the theory behind it. And then we have an equation to help us. So if you look at a balanced chemical equation, we can write an equilibrium constant, K, for when equilibrium is reached. So what's really cool is the way that these stoichiometry works out, the stoichiometric coefficients, the small numbers here, letters. If you take, here's our products. If you take the concentration of the products and then you raise it to those coefficients, and then you divide that by the concentration of the reactants and you raise it to those coefficients, when it's in equilibrium. So if this reaction is happening and the reaction is in equilibrium, and then you put the concentrations of those equilibrium items, you will get the equilibrium constant, like the K value that is only true when the reaction is in equilibrium. Okay, so what does this mean then? So first off, I want to point out it is products over reactants. So what if your K value is really big? Like look at the size of this K value, 3 times by 10 to the positive 81. That means when equilibrium is reached, because K is only true at equilibrium, that there must have been a lot of products and not very many reactants, because that would result in a much bigger K value, because this is in the numerator. That the concentration of products is directly proportional to your equilibrium constant K, and that the concentration of reactants is inversely proportional to your equilibrium constant K. So if you see that a reaction has a very large K value, that would mean that the amount of products at equilibrium, that there is way more products than there is reactants. It's opposite if you have a small K value. Look at this one, times by 10 to the negative 92. That would mean that at equilibrium, when it finally goes back and forth and it gets to equilibrium, that there's way more reactants at equilibrium than there is products, and that would result in a really small K value. When you have a relatively small, or comparable amount of products and reactants, when we have a K value that's not super big and not super small. So when we have this around between negative times by 10 to the negative 2 to 100 to 100-ish K in there, we got a relatively equal amount of reactants and products at equilibrium. So if I have this balanced chemical equation and I want to write the equilibrium expression for this, notice that this one says K sub C, and the C stands for concentration. And this is going to be really important. You're going to see why in a moment. So if I want to write the equilibrium constant for the concentration of this reaction, that would equal my products over my reactants. So here's my products. So concentration of nitrogen monoxide raised to the second, because we have a coefficient of 2, divided by the concentration of N2 and the concentration of O2. Similar to when we were doing rate laws, see how we have coefficients of 1 in front of there? So these are technically raised to the first, and then we wouldn't write the 1 down. So that is the equilibrium constant expression for concentration with this reaction. Another important thing to note, that concentrations don't change for solids or liquids. concentrations of gases change and aqueous items change. So for that reason, if something is a solid or a liquid, we don't include it in the concentration. Let me explain this. So let's say that this is my solid. And reminder, concentration is the amount of stuff, the moles, over a given volume. And if I have a solid where these things are all compact in here, look at the volume of this, okay? So here is the mass, and it's divided by the volume. If I get rid of any of this solid, I got rid of mass, but what did I also get rid of? Volume. And I got rid of half of the mass, and that got rid of half of the volume. So because whatever change in mass is equivalent to a change in volume, concentrations of solids, and this is also true for liquids, do not change. So if I have a solid or a liquid, I leave them out of these equilibrium expressions. So looking at this guy, and maybe let's draw a quick picture here. So here's my solid, and let's give it like, we're going to say it's like this is the volume of this solid, and here's the mass of this solid. So the concentration would be moles or mass. So let's do moles. Sorry, change that to an N. Here's the amount of moles of stuff, and here's the volume of that stuff. So the concentration would be moles over volume, right? And then if I get rid of half of that mass, so I'm going to draw the whole thing again, and half of it's going to go away. Now I have half the amount of moles that I did before, but guess what? I also have half of the volume that I had before. And so then that would mean that it's half of the moles divided by half of the volume. Well, half over half cancels, and so it's the same concentration as it was before. Okay, so I'm going to write the equilibrium expression for this reaction right up here. If it's a solid or a liquid, I do not include it in my equilibrium expression. We do include gases and aqueous because those can change. So the equilibrium constant in respect to concentration for this reaction would be products over reactants, concentration of carbon dioxide raised to the first because there's a coefficient of 1, divided by concentration of carbon monoxide raised to the first. Okay. There's something else that's really simple, and it's called a reaction quotient. And K, C, and QC are calculated the exact same way, where you do products divided by reactants raised to their stoichiometric coefficients. But the big main difference between these is that KC is only at equilibrium, okay, where QC is at any point. So here's what's cool. If we calculate Q and we know what K is and they're equal, like our QC value is equal to our KC value, that is only true at equilibrium. So then it'd be like, oh, it must be at equilibrium. But if Q is smaller than K, and actually I want to flip these around and I'll explain why in a moment. So we're going to say K is equal to Q, K is greater than Q. Okay, so if your K value is bigger than your Q value, then Q is trying to get to equilibrium. It's trying to be the same as K. So if we want Q to get bigger, that means we need to make more products. And so that would mean I have to favor the forward reaction. Now, look at the alligator. It's eating the K value, right? And so if you do it that way, then the arrow points to the forward where like the reactants turn into products. I'm going to give you another example here in a little bit. But if you calculate Q and you're told what K is, and it turns out that Q is bigger, the alligator's eating it, it's bigger than K, then it's got to decrease. Q is going to decrease until it equals K because it's trying to get to equilibrium. So if Q wants to get smaller, then we need to have more reactants and less products. And if we're making more reactants, that's favoring the reverse reaction. And so that's what happens to get back to equilibrium, or to get to equilibrium. Here's our alligator. We're going to favor the reverse reaction. Here's the other way that I really like remembering this. I think of it as a number line. So it's like, okay, here's my reaction, and in the middle is equilibrium. This is K, all right? And so if this is a number line, this would mean the Q is less than K, and this would be a Q that is bigger than K. And know that it's trying to get to K, which is equilibrium. So if Q is not equal to K, it's not at equilibrium, and it's going to try to get to equilibrium. And so for Q to get to K, Q is going to get bigger, or reactants turning into products. We're going to favor the forward reaction, where if Q is larger than K, it's going to get smaller, or it's going to be going to the left where products are turning into reactants, and that would be the reverse reaction. So that we are either going to favor the forward reaction or favor the reverse reaction, or we're going to favor neither. They're going to be equal. The rate of the forward is going to equal the rate of the reverse when equilibrium is met. Okay. Alrighty. So here's our reaction, and let's write our either Q or our K. We'll do Q, C. These are all gases, so then we'd have concentration of nitrogen monoxide raised to the second, concentration of N2, concentration of O2. And then they tell us what these items are. So they're saying in this vessel at this temperature, the concentration of N2 is 0.50 molarity, and the concentration of O2 is 0.25 molarity, and the concentration of nitrogen monoxide is 0.0042 molarity. And so I can plug these in to see what my Q value is. So I would take my 0.0042 squared divided by 0.5 times by 0.25. And my Q, C, is equal to 0.00014, etc., or 1.4 times by 10 to the negative 1, 2, 3, 4. All right, great. Now, it also told us what our Kc value. It says that our K value is 1.5 times 10 to the negative 3. Oh, so negative 4, negative 3. So Q is smaller than K. So let's think about this number line. Here's K. Here's Q. It's smaller than K. So it's going to try to get bigger until it gets to K, and it's going to favor the forward reaction until it gets there. So is the reaction mixture at equilibrium? No. If not, in which direction will it proceed to reach equilibrium? It's going to, which direction? It's going to go to the right, or it's going to favor the forward. So is it at equilibrium? No. The reaction will favor the forward. until it gets there. Great. Now, in addition to KCs and QCs, we also have KPs and QPs, and I'm not going to spend a lot of time on this. The only difference between them is that these are pressures instead of concentrations. So if it says KP, then you need to do the pressure. If it says KC, you need to do the concentration. Now, one thing that they're a big stickler on in the AP Chem test, if it's a C, KC, you use brackets for concentration, and if it's a KP, you use parentheses. So it's like the pressure of D raised to the D order, or, yeah. And then the pressure of E raised to that stoichiometric coefficient. So here it says write the equilibrium expression Kp. And all of these are gases. None of them are solid or liquid. So my Kp, products over reactants. So it's the pressure of NOCl. That's my product. And that whole thing is raised to the second, divided by the pressure of nitrogen monoxide, raised to the second, multiplied by the pressure of Cl2, raised to the first. So if this was a question on the AP Chem test, that's what we need to write down. If you write down this, where you do the brackets, then you're not going to be awarded the points. So be so careful with that. Alrighty. Okay. So, we have some examples of this I think we're going to do in class, and then I'm going to talk to you again just about comparing when Q is bigger than K, what will happen, which direction will we go when Q is less than K and when they're equal to K, and so we're going to practice that. There is one thing that was not in the notes that I meant to point out to you. Will you please turn back to page, let me find a good spot for this. Back to page 6, please. So go back to page 6, and this is what we're going to wrap up on. When dynamic equilibrium is reached, two things happen. One is the concentrations of these reactants and products stop changing. And so that's what we saw here, that these concentrations, the amount of both the reactants and the products stopped changing, okay? So sometimes they're going to show you a graph, and these graphs are concentration versus time graphs. So like concentration versus time graphs. And typically our reactants start off really high, and then they decrease, and then they like level out. And so that's like our reactants. And usually with products, they start off really low or zero, and then they increase over time, and then they level out. Okay. Sometimes they crisscross, sometimes they don't. But what I need you to know that when they equal each other is not equilibrium. At no point did my amount of reactants equal my amount of products. It's when the amount stopped changing, when the concentration stopped changing, when it became constant. So on this graph that I just barely drew, equilibrium was established about right there. When the concentration, the amount of these things stopped changing. And the reason why they stopped changing is because the rate at which the reactants were turning into products equaled the products turning back into those reactants. That if one of each of these items became one of those, and then one of these things at the same time went back to one of each of those, then it's the overall didn't change. The other thing you might see is a rate versus time graph. This is rate, not concentration, versus time. And typically the forward reaction is higher than the reverse at first, and then the rate of the reverse reaction increases and the rate of the forward decreases, and then they equal each other. So this is the rate of the forward reaction, this is the rate of the reverse reaction. Not concentrations, rate. When these equal each other, right here, that's when we reached equilibrium. Okay, more on that later. Thank you guys for your hard work, and I'll see you all in class.